A forewarning for this video. I was doing the editing and there are so many things wrong with this video. I am ready to just throw the whole thing out, but there's some good stuff in here, so stick around just because maybe you'll be entertained by an engineer's crazy attempt at chopping up poorly planned out footage about a vacuum design and his theory about stuff. Hello everybody, I want to talk about vacuums today because I have some cool things to share. Maybe you've noticed throughout my videos of lab equipment and designs that I have these colored rings around all the vacuum tubes, okay, including the shop vac and the portable vacs, etc. And so that was the beginning of an evaluation period. So I wanted to solve vacuums for everyone, and I think I did that. I did that last year, and now I just have to tell everyone about the solutions for change to happen. And so thank you so much for giving me your attention on that. Let's start at this quick spreadsheet. Why is it crucial to solve vacuums? Why is it such a high priority that in the middle of building up a robotics company, I would offer my time to study vacuums? So we're looking at the energy consumed by power tools. And so this is a subsample of most of the tools that I work with every week here in the lab. This is for building things and for evaluating or designing robotics contraptions. All of the stuff in mechatronics is merging together. That means something may be a tool today or it may be a part of a robot tomorrow. And over here, blower and wet vac, these are the top power draws, measuring between the battery and the machine itself, how much power is being pulled. So we're looking at 300 watts and up for just to have that machine on. There is no condition like the idle condition or freewheeling condition of a grinder. When you're not cutting, the power can drop down near 100, etc. for the other tools. The blower is always doing work. Vacuuming it's power intensive. So performing suction and moving air takes a lot of power, and there's no way around that. There's no technology that can make it take less power. We're talking about the AC machines or the DC machines. We have our elephant machine here. So when I use my power tools, I always equip this vacuum with the highest amp hour battery. This will drain a 6 or 8 amp hour battery faster than my drill. My drill, sometimes I could go a whole week just with the 2 amp hour battery. And versus this one, I get 30 minutes of use out of it. If we want to build automated things like this vacuum, then we need to make that machine cordless. And so that's going to mean that we're going to include a battery in it. And that means that we need to budget the power. Out of all different types of mechanical functions, moving air is probably the most power intensive task that you can do. And I'll show you how they've modified this vacuum to make it happen. Let's do a quick interlude so I can join together the topics that you're hearing right now. It's airflow, automation, and robotic things. You're looking at a pathway to automation, and I would suggest, as an advisor, I would say this is the pathway to automation. You have an appliance. The first step is to make that into a cordless appliance. The next step is to give it digital control rather than analog. And the following step is to give that feedback control, which really consists of a sensor and decision-making power. So there are 3 steps here, and then you have an autonomous appliance that's a robot. Okay, then we come from the pathway down to the steps inside that pathway. It's just a reiteration of these 3 steps. Make it cordless, make it digital, and give it feedback. I think that number 1 is the most effort intensive. So diagrammatically, we've got it shown here, 3 steps. biggest effort is number 1. So what's inside of number 1? We have these. Make the appliance DC, add a battery, and then perform energy budgeting for that battery. So you have the diagram here. This is broken out to those 3 steps. I think number 3, budgeting energy, is the most effort intensive. And then we have number 1.3 broken out into a few different pieces. That is, we're budgeting energy for moving heat, moving solids, moving liquids, and moving air. Those are the only things that consume energy. And then we have those drawn into a diagram, and I would suggest that 1.3.4, moving air, is the most energy intensive. That's what brings us to the vacuums as a worthwhile focal point for developing robotics. And so when you look in an autonomous vacuum like this, they've already, to make it last longer, they've reduced the power of the vacuum as much as they can while maintaining effectiveness. And these rollers and this brush, so I could make an autonomous vacuum that sucks up this very wide path, but instead they're saying, well, let's direct the dust into a smaller path so that we only need to vacuum a small zone. And ultimately, they're kicking up the dirt mechanically because that takes less energy, and then just finally getting it into a position where the vacuum just has to do a little bit of work. So the vacuum does 2 things. The blower motor on this system does 2 things. So 1, it takes the dust and dirt against gravity up in this path. It doesn't pull dust and dirt from this zone. That's what the kicking action does. And number 2, so that's one resistance, one work that the vacuum, the airflow is doing. And the other work that the airflow is doing, that is resistance to pushing a force against resistance, is to push the air through this resistive panel, whatever. So it's that you have a filter, but all this pathway is free and open. It's not requiring much work to perform the airflow, but this zone is, as is the fine screen there. I'm probably getting too deep. I'm gonna back up out of the deep technical weeds to get to the topic I wanted to get to. That discussion probably appeals to technically interested people, but what about the general public? That's the message for the general public, is just this. It's that if we understand the diameters and the fitments of our equipment between one vacuum and another, then we can save millions of dollars and get things working better the way they ought to, even if you've lost parts. What a wimpy and unconvincing way to explain that. I'll give you an example. So you look at the jigsaw. It has this port in the back, that little hole, okay? And the jigsaw came with, and when it was brand new in the box, it came with a little tube attachment thing that's actually carefully designed. That gives you a place to hook up a vacuum if you want to, but there's no, by default, it's not necessary to use it. Well, what happens? When I'm going to cut a line on some wood, etc., the sawdust piles up right in front of the line, and then all of my cuts become that much less accurate. And if I did, where is that thing? Why have I lost my attachment? Because I stored it away, because it wasn't useful. Why was it not useful? Because it was, it was useful, and it just wasn't convenient for me to have a vacuum hooked up to it. But suddenly, when I get all my vacuum stuff working, everything becomes convenient, and then you gain back the benefits of all the stuff that was ready to benefit from convenient, nice, sealed, good vacuum tubes. I'm saying from personal experience, you probably don't know all of the loads and loads of benefits that you'll get from getting your vacuums convenient and working. And you've probably forgotten all of the opportunities where it's going to come back into play and it's going to make everything better. We can get ourselves more options and modularity. And so this is an adapter that I 3D printed. It's a very, very simple geometry, but it does an important thing. All of these attachments back behind me, they have the red tape. That meant it was nominally 35 millimeters. And a great deal of shop vacs just have this same nominal diameter, and I say nominal, I'll explain that in a moment, for their tubes and attachments. So when you pull it out of the box and you compare it with your old vacuum from years back, maybe it doesn't seem to fit. It has some contraptions like clip things. It doesn't seem to all go together, but it does if you examine a number of things. And so I'll direct your attention to that, and you can probably gain lots of good benefits. Okay, we're looking at a vacuum hose connector or tube connector. This is the sliced, and this is when it's pointed towards you. So this is the female. And the female has its inside diameter makes contact with the outside diameter of your male. Okay, so that's a pretty obvious type of designation. The black part here is the female, and this is the male. And so that's just F and M. And then we have a nominal diameter is what we can use to describe both both female and male mating configurations. And I'll tell you what makes it a little more complex next. So we said in this form of the drawing, male is here. I'll show you examples with parts. So if we want to measure our pair of fitments, then this is actually 4 diameters you can measure. The one out here, the one in here, the one out here, the one in there. And then they have a conical shape, and so the diameter is not consistent. So right off the bat, you imagine, if you're a designer like me, you're imagining, oh, well, each brand has its own type of conical, the rate of the slope or the cone angle. So it was not of interest for many years, just thinking that they wouldn't work together, but they do. Okay, so we come down here and look at this is the rigid portable vacuum that's battery powered. We have the red on this part and the red on this part, but they are not the same diameters. Obviously, the right hand here is bigger and the left hand is smaller. This is what I call the 35 millimeter nominal diameter. And then you may have many different varieties of shapes on this end for this type of attachment, that they can vary in a number of ways and still fit. But approximately, you can measure the inside of here and find 35 millimeters. And you can measure the outside of here and find 35 millimeters. I'm going to double check that it's not 45, since I finished the project, so I may be wrong. Okay, so we get here what I'm calling 45. If up near the tip, it's less than 45. Back near the base, it's above 45. We have around a millimeter increase, 44.5, 45.5 millimeter increase across that. So now you could start to get into calculating the slope and so forth, but that's the stuff that I already did and included in Designs Online. So now we have, if you want to connect any of your smaller attachments to this type of gadget, you can, of course, you can go and find the compatible adapter and purchase that. But the adapters stack up over time. It's really nice to just understand your own fitments and then provide your own, label your own, or buy it once and never again. So now we come down here. I'll just take the camera off the tripod. You have all these that came with another brand of vacuum. They're all blue because they have the 32. 2 is blue. And it's like, oh, sometimes I want these stiff, fine bristles, to, get into grooves of things while I'm working. Why can't I have this on my other vacuum? Of course, you can with the right adapter. Which parts do you need to know about this design? Okay, so I would recommend go through your vacuum equipment. Some of the things that belong in the home are better off in the shop. Some of the things in the garage are better off in the home. And you should be, as the consumer, you should be the one who's doing the work and deciding where do you want to have these different functions. This is like something that may be provided with a car cleaning kit for a fine nozzle. But what if it all worked wherever you want? That would be the starting point for you to have control of your all of the work that you're doing. So you will notice as you're measuring, if you look at the female variety of these smaller tips, 32 is a very, very common standard. And only when you get into more odd or unique, I think the Shark had a bunch of equipment that was 36, and basically I just set that off in storage after I realized that's very uncommon. And I need fewer parts because things are complicated enough as they are. Okay, so you come to the Eureka, we find that its main hose has the 32 male. So then you're going to start to notice commonalities between all of the different brands and how you can start to interchange them. That would be, so first point was that we have 35 common, 35 and 32. 45. 45 and 32. I bet 90% of household equipment has this, even if it's from Home Depot or Walmart or Target or online. That's very common. That gets you things divided into just two, and then you have male and female, and then you have the direction, because things actually, all of this gets broken if the design is reversed, and I'll tell you why. Let's just consider a typical system to be part one, that's the hose that comes with your machine. Part two, that's an extension that comes with your machine. And part three, and that's a tip that comes with your machine. So now we need the sizes to match up and the male versus female to match up. This is a golden nugget here. They almost always place the female at the beginning of the flow path, the airflow path, and the male at the next step. So wherever your attachments are, that is fairly standard, and so that's great. What I mean by that is that the item further down your tube will be the female that mates to the male on your tube or your extender, and I'll show you. Oops. Oh no, you're not supposed to drop those on the floor. Okay, so a long attachment. This is a weird one. This is an example of a part I would probably throw out because it's too odd for the rest of the systems. Where did I put my extensions for the... Oh, there's more here. Okay, so I'm still needing to build more supply racks for these things, but the most common ones are available right away. Yes, I've got adapters and extra pieces in here. The purple one was 8, I think it was 48 nominal, and that one exists for the larger, heavier shop vac stuff, but it's just not been needed ever since I took care of the first 2 diameters. All the attachments and tubes do what I need them to do. Okay, so you have an extension. That's a little over a foot or so. Okay, you have 32 there, and you'll notice now I'm sliding in further in this configuration than on the last pair that you saw. And so, yes, you measured this one and it's way down at 30 and you're thinking, oh, is this an odd one? Does it maybe not fit? Well, it still does, because that's something you'll find differences from brand to brand. But ever since I got the nominal designs set up for this parametric part, and I'll go into that next, we just select 35 or 32 on each end, and we select male or female on each end. Okay, so I wanted the 32 female here, then it fits every single blue marked part in the lab that I have, and no matter which brand. And I think I've worked with over 8 or 10 brands. The next thing to look at is your actual tools, because many of the brands also contain tools that will come with a little bag that attaches, or for your convenience, they're implying here that you can connect the hose of their same brand's vacuums, or even their larger vacuum won't fit, and so you have to buy the smaller one. It's crazy. We can solve most of this. So inside of these appliances, you have some airflow generating system. So on the same motor that spins this disc, there's also a small fan. And so it generates airflow, and you have that expelling the debris and air through this tube, but they'll create some confusing geometry sometimes. Sometimes it's there to help you, and sometimes it's there, it's a poor design decision, and they're just not falling in line with the other brands. So this one has two options. You have the small vacuum that I can hook up here. Okay, so this is the Shark vacuum machine, because it's amazing performance, and it's HEPA grade. You don't throw debris around the shop. And then, so I've got a rigid branded hose, because that's the one I liked the best. It's more flexible and doesn't get scratched and dirty so easily. Okay, so I can hook that up directly. All you have to do is take a look at the cavity of your tool and say, okay, well, I'm not going to have any airflow coming out of here, so I won't have debris if I haven't covered the large diameter. Great. So now I have this called, let's say this is 1 cubic foot per second of airflow out, but this thing will pull 10 times more airflow. So you'll get better performance sanding, better performance having clean air. And the higher flow doesn't damage anything, doesn't hurt anything. It actually takes load off of this motor that's trying to move the air. So, I mean, theoretically, your battery would even last a little bit longer while you're using this machine. Great. And so then if we can get this portable, we can do the work anywhere we need to. And when it comes to safety concerns, like in university labs, we're not permitted to just generate dust in the middle of a classroom or something like that. So if you want to bring things outside, now we have the full portability taken care of, even if I didn't purchase the rigid brand hoses and things. So we come over here, and first day I unboxed that sander, I said, okay, does my ordinary rigid, see, I've 3D printed this little clip here so things can be carried around easier. I might need two hands for that. So you'll try this out. You'll grab the brands you thought would work together, the models you thought would work together, and then you say, oh, this is a male 45, red is 5, and no, it doesn't go. It sort of does, and then you try it, you wonder if the design was intended for that, and it kind of stays until you reach one moment and it yanks on this, and then you just blow dust everywhere. So we don't have to settle for things sort of kind of working. We have, this adapter says I'll go from a male on the 32 towards the female 32, and then I'll have a female that clasps the female here. And you'll notice, okay, in this case, it's only inserting maybe 5 or 10 millimeters, but that's firm and that's fixed. And when this system is under pressure, like negative pressure, it's a force that helps actually keep those together. I've never had things just slipping out ever since I designed and printed out these adapters. And first I had printed a couple dozen different variations thinking that I needed those, and the variations came down. Over time I realized, okay, if I conform to female clasps onto male machine or male the next in the series, then I can throw out some of those. And I simplified and simplified, so until what you have right now. Now, if the viewer here wants to build their own and solve their own issue, they can choose whichever diameter they want, because that's the part that I published is parametric, and you just select a diameter and it's going to automatically generate that contour. I'll show you where that is. Okay, I'm going to talk about the design just very briefly and then wrap up the video. What I'm calling open source and parametric, this is very rare and it needs to become more common. So open source, you at first thought, you may think if I've provided the STL file, then everyone can download that file, stick it in their printer and print it, or order it at a printing service online. A fixed geometry. It's not going to be changed. These people are not designers. They are just end users, okay? Or even maybe they're selling them. So they could start a whole business based on it, but they're not designers still. Then you have the source of the STL actually was a SolidWorks model that has a whole feature tree. This is relevant to be shared to other engineers who may actually enhance the design and refine it further, or make more parametric functions out of it. Then you have the step file, which also is relevant for designers who do not use SolidWorks. They use another software, but they want to find true resolution geometry that the STL does not give you. And true open source means we're going to share all of the source, not just one piece. That's one thing. And then also parametric, there are parametric functions that are built into the feature tree here that give a lot of freedom and a lot of benefits to these engineers who may be working with the part. And that is only available with the native designs. So I'll talk more about that in the context of parametric designs in another video. One more note, something very strange happened while I was making this video. I went to go look for the model that I had posted around a year ago. This was already uploaded on GrabCAD online with all the files, SolidWorks, STL, etc., as photos, etc., and it had vanished. So if I went through my GrabCAD uploads, it was no longer there. There was no notification that something got taken down, etc. That's very strange, but it is another clue for us that the economic impact of making a simple device that adds value for millions of people, this could have enormous economic impacts. And they're not going to sell as much garbage to people if we solve our own problems. So we're going to make this persistent, though. As many of you know, I am consistently uploading more content, designs, methods, and even some links to these videos in the OpenLab project. And so this is a GitHub-based web page, qr.net/OpenLab project. So you can punch that in. If any links get broken, I go up to my YouTube bio, and you can look inside the YouTube bio to find these links. If anything's broken, I'll put the latest there. But this is the documentation of all the equipment and methods in the lab. There's the tour, and that's starting to be documented. This one is under methods. So off the print parts, this section is going to have parts such as this vacuum nozzle thing. And so no matter where it gets taken down off the internet, in these privately owned business websites, I will find a way to keep it maintained and offered elsewhere. So you'll have a description. You'll have basically the core information about why it exists, what it does, that will be maintained inside of OpenLab project. So just a few snippets and then a link to the GrabCAD. We'll see if it vanishes again. And then also, as I'm expanding this web page with more and more information, it can be hard to find things. I'm still discovering the best way to organize, but there's a wonderful, wonderful tool. That's that search bar. And so this is one of the reasons I put the descriptions here, is because if you want to look up vacuum, then you get instantly returned results for anywhere on the website. So let's go to the home. Oh, come on, home, and then I type vacuum. Then you can go here and it will find the part of the page. So please utilize the search function if you need any of this stuff, and then refer to this page. If you're using this page to discover materials and you have questions in the videos, feel free to mention, reference what you're asking about in the context of OpenLab in the YouTube comments. Thanks everyone. Let's wrap it up here.